In this video, we're going to talk about the idea of concentrations. So a concentration is just how much of something is present. But it kind of depends how you discuss it. If you are one person sitting in one chair, then you've probably filled your chair. But if you're one person and there's 20 chairs, well, you probably haven't filled your chairs. You have just as many people. But because you have a larger volume of chairs, you're not occupying as much of it. Concentration comes down to how much stuff is present in your container. And so if we have a container we fill with water, and it's got 3 things in it. Usually we use moles, so it'd be 3 moles, and usually we use liters, so it'd be 3 moles per liter. But the idea at the moment is just, I have 3 things in my one container. If I made a second container of the same size, and I put 3 things in it again, I filled it with another same amount of water, well then collectively, I went from, well, we'll say 1 liter and 3 mole, and another 1 liter and 3 mole. My total is now 2 liters of space and 6 moles of things. So 6 green dots, 2 containers. Well, if I said, all right, well, how many is in each? Well, it's still 3. The fact that I have twice as much doesn't change the fact that there's still only 3 dots per container because I have 2 containers they're spread out in. And if I made 1 container that's just twice as big, and I poured both of those into it, I said, hey, my first one, pour you into there. Second one, I'm going to pour you into that container. And let's just assume that container was the correct original size. There we go. If I pour my 2 separate containers in, then what I have is a single container that has the sum of both of them. 2 liters of volume, 6 moles of stuff. Moving them between different containers, spreading it over 2, doesn't change how much I have. Concentration is just the amount of stuff I have in a volume. What if I had one of those containers, and instead of spreading it out, I put all 6 things into it, but it's still only a 1 liter container. In this case, I'd have 6 moles of stuff, but 1 liter. Well, in this case, I have twice as much stuff in the same space. If I was to double this and also put in more things, I'd have another 1 liter and another 6 mole. Our right one has a larger amount than our left one. Our right side has 2 liters of volume still, but now it's got 12 moles of things. There's just twice as many things floating around in there. Concentration is how much over your volume. If you make your volume bigger for the same amount of stuff, well, let's try that again. If I've got 1 container here, 3 dots, so it's 1 liter, 3 mole. But if I have the really big container, and I transfer my particles over along with their water, so whatever water would have fit in here, we could transfer that, and then I add more water. Well, those individual particles can float. They can spread out. And what I end up with is 2 liters of total volume with 3 moles. Well, this really just looks like, if I cut it down the center, a 1 liter with 1.5 mole and a 1 liter with 1.5 mole. Kind of did it right over the top of it, but we can cut right through there. If I look at the whole thing, I say, oh, there's 3 liters and 2 moles. But if I look at any half, it's half of both. I get half as much stuff in half the volume. Concentrations, as long as it's the same container, they don't care how much you're looking at. So if I have 3 moles in 2 liters, that's the same as 1.5 mole in 1 liter, which is the same as 0.75 mole in half a liter. Same as 6 mole in 4 liter. If you do these divisions, 6 divided by 4, 3 divided by 2, 1.5 divided by 1, 0.75 divided by 0.5, you'll get the same number back out. These are all just cutting our bigger container into smaller bits. When you do that, there's still the same ratio of material, which is really what concentration is. It is a ratio. It is a ratio of moles or amount. It might be in grams. There's a lot of different ways we can do it. But is the ratio of an amount of something over the volume that it is contained in. Where this becomes useful is if you have a giant container and it is just filled with liquid and just filled with material. Well, actually going and counting up how many green dots I just added would be very difficult. But assuming it's spread out evenly, you could cut out one small spot. You could say, hey, this was 1 liter and it had 1 mole of stuff. If you are told, or you can measure the tank and find out that the tank is 35 liters, well, how many moles of stuff do you think you have? The beautiful part about a solution is it spreads out evenly. Solutions are homogeneous. Every region should have the same mixture. So like a can of Coke, if you sip off the top or you sip off the bottom, it tastes exactly the same. Everywhere in this container, on average, should have exactly the same amount of stuff. If I pick any other random 1 liter, it ought to have the same amount of things in it. And so if 1 of the liters had 1 mole, in 35 of the liters, there should be 35 mole. That ability to scale up both the top and bottom, or scale down both the top and bottom, so that we can work with reasonable volumes, is a cornerstone to the use of concentrations. Where we end up using this is if you had 5 grams of compound X in 100 milliliters of solution. And it was just sitting in a bottle. So I got a bottle. There's some X floating around, doing its thing. And then you pour it out. Or you get a bowl or a cup. And you take it and you say, hey, I'm going to scoop it up here. And I'm going to pour some of this out. And now you have some material in there. I stole some of the big container. Well, if there is 10 milliliters of the solution over here, I have 1/10 of the total volume, which means I will also have 1/10 of the total mass. Because I can say that, hey, if there was 5 grams of the compound in 100 milliliters, well, scale. In 1/10 milliliters, there should be some amount. You could figure it out. You could multiply this on both sides so that you reorganize it. 5 times 10 divided by 100, you'll find that the question mark will equal 0.5. 0.5 grams in 10 milliliters is 5 grams in 100 milliliters. Both the top and bottom are just 10 times larger. Or if you're doing it on the left side, 10 times smaller. You can keep scaling it up. 50 grams in 1,000 milliliters. Or scaling down. 0.5 grams in 1 milliliter. By knowing what the original container contained, if I take any volume out of it, I can find how much is in that new volume. Or conversely, if I know a weight I want to take out, I can figure out the volume I want. If I want 2 grams, there's going to be some milliliters that will have that. Well, I know there's 5 grams in 100 milliliters. So we could reorganize this, multiply our milliliters up, divide our grams down, multiply the other milliliters up. 200 divided by 5 is going to be 40. What we could find is I would need a chunk, a container, 40 milliliters in size. I could scoop that inside, and then it could pick up that material. What volume would have 2 grams out of this starting solution? We can solve it. And we'll do a lot of math with this in the section on calculating concentrations. But this is just the idea of what the concentration is telling us. It is a ratio. And we can take the ratio we were given and we can say, well, if I scale it up, it'll be this many grams in this many milliliters. If I scale it down, it'll be that many grams in that many milliliters. And we can even find specific volumes that will give us grams we need for a reactor. So this is the idea of concentration.